Welcome you all. In this session, we discuss the Poisson distribution. A discrete random variable capital X is said to follow a Poisson distribution if the probability mass function of the variable x is defined as f of x is equal to e raised to minus lambda raised to x divided by x factorial, where x is equal to 0, 1, 2, 3 etc. up to infinity and 0 otherwise. Here lambda greater than 0 is the parameter of the distribution. The Poisson distribution is used in order to specify the probability of a very rarely occurring event. We have to verify this defines a probability mass function. We know that f of x is a PMF if and only if the two conditions hold. First one is f of x is greater than or equal to 0 for all values of x, and summation f of x is equal to 1. This is the second condition. Here lambda greater than 0 and x is equal to 0, 1, 2, 3 up to infinity. If we put x equal to 0, we get f of 0 as e raised to minus lambda, because lambda raised to 0 is 1, 0 factorial is 1. E raised to minus lambda is greater than 0, not negative, which is always greater than 0. Similarly, f of 1, f of 2 all are greater than 0. Therefore, the first condition holds, and we have to check this condition. Summation f of x is here, summation f of x is equal to f of 0 plus f of 1 plus etc. plus etc. up to infinity, which is equal to f of 0 is e raised to minus lambda plus f of 1 is e raised to minus lambda into lambda raised to 1 divided by 1 factorial plus e raised to minus lambda into lambda square divided by 2 factorial plus etc., which is equal to e raised to minus lambda into e raised to minus lambda can be taken outside. Therefore, this is equal to e raised to minus lambda into 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus etc., which is equal to e raised to minus lambda into, this is the binomial expansion of e raised to lambda, that is e raised to minus lambda plus lambda, that is e raised to 0, which is equal to 1. Therefore, both the conditions for a PMF are satisfied by this function. Therefore, this is a PMF. Now, the expectation of Poisson distribution is the parameter lambda itself. We have to show this. By the definition of expectation, E of x is equal to summation x into f of x, where x is a random variable having the Poisson distribution, which is equal to summation x varies from 0 to infinity, x into f of x is e raised to minus lambda, lambda raised to x divided by x factorial, which is equal to summation. Here if we put x equal to 0, the corresponding term will become 0. Therefore, the variation can be taken from 1 to infinity x into this e raised to minus lambda can be taken outside, because the summation for x, e raised to minus lambda into summation from 1 to infinity x into lambda raised to x divided by this x factorial can be written as x minus 1 factorial into x. So that this x and x cancelled. This is equal to e raised to minus lambda into, if we put x equal to 1, we get lambda raised to 1 by 0 factorial plus next value of x is 2. Therefore, this is lambda square by 2 minus 1 is 1 factorial plus lambda cube by 2 factorial plus etc., which is equal to e raised to minus lambda into, here all the term contains lambda, therefore, lambda can be taken outside. Therefore, this is equal to e raised to minus lambda into lambda into 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus etc., which is equal to e raised to minus lambda into this is the binomial expansion of e raised to lambda. This is equal to lambda into e raised to minus lambda into e raised to lambda is e raised to minus lambda plus lambda, that is e raised to 0, e raised to 0 is 1. Therefore, the expectation of a random variable having Poisson distribution is lambda. Lambda is the parameter of the distribution. That is the arithmetic mean. Expectation means the arithmetic mean is lambda. Now, we have to find the variance of x. Let x follows Poisson distribution with parameter lambda, then f of x equal to this. By definition of variance, v of x is equal to, variance of x is equal to expectation of x square minus expectation of x the whole square. We already obtained expectation of x as lambda, e of x is equal to lambda. Therefore, we have to find this term e of x square. Now, e of x square is equal to expectation of x square minus x plus x. That is, we just added an x and subtracted the same from x square. That is equal to expectation of, from here we can write x into x minus 1 plus x. This is equal to, we can split into two expectations, that is expectation of x into x minus 1 plus expectation of x. Expectation of x is lambda. Therefore, we have to find expectation of x into x minus 1. By definition of expectation, e of x into x minus 1 is equal to summation over all x into x minus 1 into f of x, which is equal to summation x varies from 0 to infinity x into x minus 1 into f of x is e raised to minus lambda, lambda raised to x divided by x factorial, which is equal to summation for x. Therefore, e raised to minus lambda can be taken outside. This is equal to e raised to minus lambda into summation. Here, if we put x equal to 0, the corresponding term will become 0, and if we put x equal to 1, the term corresponding term will become 0. Therefore, we can take the variation of x from 2 to infinity, that is e raised to minus lambda into x varies from 2 to infinity, x into x minus 1 into lambda raised to x divided by x factorial can be written as x minus 2 factorial into x minus 1 into x. Therefore, this x into x minus 1 and x into x minus 1 will be cancelled. Therefore, this is equal to e raised to minus lambda into, on expansion we get lambda square divided by 0 factorial plus lambda cube divided by 1 factorial plus lambda raised to 4 divided by 2 factorial plus etc., which is equal to e raised to minus lambda into, here all the terms contains lambda square. Therefore, lambda square can be taken outside. This is equal to e raised to minus lambda into lambda square into, here 1 by 0 factorial, 0 factorial is 1, therefore 1 plus lambda by 1 factorial plus lambda square by 2 factorial plus etc., which is equal to e raised to minus lambda into lambda square into, this is the expansion of e raised to lambda, therefore, expectation of x into x minus 1 is equal to lambda square. This is equal to lambda square. And expectation of x square equal to, we substitute expectation of x into x minus 1 is equal to lambda square in this expression. We get e of x square is equal to lambda square plus expectation of x is lambda. And therefore, variance of x is equal to e of x square is lambda square plus lambda minus e of x the whole square is lambda square. This is equal to lambda square minus lambda square is 0, which is equal to lambda. That is variance of x is equal to lambda. We just proved expectation of x equal to lambda. Therefore, in the case of Poisson distribution, the expectation of x and variance, expectation of x means the arithmetic mean, and the variance of x coincides. Mean of x equal to variance of x is equal to, both are equal to the parameter lambda. Now, the moment generating function of Poisson distribution is, by definition, moment generating function is mxt, which is equal to expectation of e raised to tx, which is equal to summation e raised to tx into f of x over all x, which is equal to summation x varies from 0 to infinity e raised to tx into, here f of x is e raised to minus lambda, lambda raised to x divided by x factorial, which is equal to summation x varies from 0 to infinity here e raised to t x means e raised to t the whole raised to x into lambda raised to x. Therefore, we can write lambda e raised to t the whole raised to x into e raised to minus lambda divided by x factorial, which is equal to e raised to minus lambda into one expansion we get lambda e raised to t all raised to 0 means 1. 0 factorial is again 1. Therefore, 1 plus when x equal to 1 we get lambda e raised to t raised to 1 divided by 1 factorial plus next term is lambda e raised to t square divided by 2 factorial plus etc. This is equal to e raised to minus lambda into, this is the binomial expansion of e raised to lambda e raised to t, that is equal to e raised to lambda into e raised to t minus 1. That is the moment generating function mxt is equal to e raised to lambda into e raised to t minus 1. From this moment generating function, we can find e of x square, and hence the variance of x. E of x and e of x square can be obtained by differentiating the moment generating function and by putting t equal to 0. Now, we can show that the Poisson distribution is a limiting form of binomial distribution. The binomial distribution is already discussed in the previous session. Under the conditions n tends to infinity, that is n is very large, p tends to 0, that is p is very small, and n into p is a constant, say lambda, then the binomial distribution tends to Poisson distribution. To show this, consider a random variable having binomial distribution with parameters n and p. Then f of x is equal to n choose x, p raised to x, q raised to n minus x, where x varies from 0, 1, 2, 3, etc. up to n. This is equal to, here p lying between 0 and 1, p plus q is equal to 1. So, that q equal to 1 minus p, which also lies in between 0 and 1. By definition of NCX, we have n factorial divided by x factorial into n minus x factorial, p raised to x, q raised to n minus x is 1 minus p raised to n minus x. P plus q equal to 1 implies q equal to 1 minus p. Therefore, we substitute 1 minus p for q. This is equal to n factorial is 1 into 2 into 3 into etc. up to n. The previous term is n minus 1, here n minus 2. In general, we can write n minus x. Here n minus x minus 1. That is n factorial is 1 into 2 into 3 into etc. n minus x, here n minus of x minus 1 etc. n minus 1 n. divided by x factorial into n minus x factorial. Into p raised to x here p is equal to the condition is n into p equal to lambda. This implies p equal to lambda by n. Therefore, p raised to x means lambda by n raised to x into 1 minus p raised to, that is 1 minus lambda by n raised to n minus x is raised to n into 1 minus lambda by n raised to minus x, which is equal to, here 1 into 2 into 3 into etc. into n minus x means this is n minus x factorial. Therefore, this n minus x factorial and this cancelled. The remaining terms are n into n minus 1 into n minus 2 etc. up to n minus x minus 1. Divided by x factorial. Here lambda raised to x divided by n raised to x into 1 minus lambda by n raised to n into 1 minus lambda by n raised to minus x. Now, we take n outside from each of these terms. We get n into, this is the first n. We take n from here, we get n into 1 minus 1 by n. We take n outside from this term also, we get n into 1 minus 2 by n. The next term is n into 1 minus 3 by n, etc. This term is n into 1 minus x minus 1 by n, all divided by x factorial into lambda raised to x divided by n raised to x 1 minus lambda by n raised to n into 1 minus lambda by n raised to minus x. This is equal to, here there are x times n multiplied, n into n into n into etc. to n. This n is for x minus 1. Therefore, there are total x times n multiplied, that means n raised to x into 1 minus 1 by n into 1 minus 2 by n into etc. into 1 minus x minus 1 by n divided by x factorial into lambda raised to x divided by n raised to x 1 minus lambda by n raised to n into 1 minus lambda by n raised to minus x. This n raised to x and this n raised to x cancelled. Now, we apply the limit as n tends to infinity. This is f of x. Now, if we apply the limit as n tends to infinity, we get limit n tends to infinity f of x is equal to limit of this product, that is limit n tends to infinity 1 minus 1 by n into limit n tends to infinity 1 minus 2 by n into etc. into limit n tends to infinity 1 minus x minus 1 by n into, here lambda raised to x is independent of n. Therefore, that term can be taken the outside of the limit, that is lambda raised to x is a constant which can be taken outside of the limit. This into limit n tends to infinity 1 minus lambda by n raised to n minus lambda by n raised to n into limit of this limit n tends to infinity 1 minus lambda by n raised to minus x. This is equal to all divided by x factorial is here, which is independent of n. Therefore, that can be taken outside of all the limits. This is equal to lambda raised to x by x factorial into limit of this term is 1, as n tends to infinity, limit 1 minus 1 by n tends to 1 into this is also tends to 1 into etc. into 1, this also 1 into limit of this is limit n tends to infinity 1 minus lambda by n raised to n, here in the denominator n, also in the exponent. Therefore, limit of this is that is limit n tends to infinity 1 minus lambda by n all raised to n is e raised to minus lambda into limit of this is 1, which is equal to e raised to minus lambda into lambda raised to x divided by x factorial. That is limit n tends to infinity f of x is equal to e raised to minus lambda into lambda raised to x divided by x factorial. Here f of x is the PMF of a binomial distribution. This is the probability mass function of a Poisson distribution with parameter lambda. This is the PMF of a Poisson distribution with parameter lambda. That is, we proved that the binomial distribution tends to Poisson distribution under these three conditions, that is n is very large, p is very small and np equal to lambda is a constant. In statistics, n is large means if n is greater than 40, it may be considered as a large sample. Therefore, when n is large, p is very small and the n into p is a constant, the binomial distribution tends to Poisson distribution. Now, we have to do a problem as an example of this case. If 0.8% of the fuses delivered to a factory are defective, then find the probability that at most 4 fuses will be defective in a random sample of 400 fuses. Here consider the success as a fuse is defective. We are given that 0.8% of the fuses are defective means the probability of success p equal to 0.8% means 0.008. Here the sample size is n is equal to 400, which is very large. Therefore, we can approximate this problem as a problem in the Poisson distribution. Here n into p is equal to 400 into 0.008, which is equal to 3.2, which is taken as lambda. Therefore, the probability mass function f of x is equal to e raised to minus lambda raised to x divided by x factorial, that is the PMF of Poisson distribution, which is equal to e raised to minus 3.2 into 3.2 raised to x divided by x factorial, where x varies from 0, 1, 2, 3 up to 400. Now, the required probability is probability that at most 4 fuses are defective means let x be the number of successes. Therefore, x can take values 0, 1, 2, 3 up to 400. We want to calculate P of at most means maximum 4, that is x less than or equal to 4, which is equal to probability of x is equal to 0, 1, 2, 3 and 4. This is equal to P of x equal to 0 plus P of x equal to 1 plus P of x equal to 2 plus P of x equal to 3 plus P of x equal to 4. That is f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4, which is equal to f of 0 is this is our f of x. Therefore, f of 0 is e raised to minus 3.2 into 3.2 raised to 0 by 0 factorial plus f of 1 is e raised to minus 3.2 into 3.2 raised to 1 by 1 factorial plus e raised to minus 3.2 into 3.2 square divided by 2 factorial plus e raised to minus 3.2 into 3.2 raised to 3 divided by 3 factorial plus e raised to minus 3.2 into 3.2 raised to 4 divided by 4 factorial. That is equal to e raised to minus 3.2 is common. This is 1 plus here 3.2 plus this is 3.2 square by 2 factorial is 2 plus 3.2 cube divided by 6, because 3 factorial is 6, then 3.2 raised to 4 divided by 4 factorial is 4 into 3 into 2, that is 4 into 3 is 12, 12 into 2 is 24. On simplification, we get the value as this is equal to 0.781. That is probability of x less than or equal to 4 means the at most probability that at most 4 fuses delivered are defective out of 400 is 0.781. This is a binomial problem, but here n is very large and p is very small. Therefore, we can approximate this binomial problem as a Poisson problem, and we use the PMF of Poisson distribution, and we evaluated the corresponding required probability. Now, let me conclude this session. In this session, we just discussed the Poisson distribution and the mean and variance of Poisson distribution. Also, we discussed the moment generating function. We proved that this Poisson distribution is a limiting form of binomial distribution under the conditions n is very large, p is very small, and n into p is a constant. Thank you for listening the class. Have a nice day.